we will discuss the basic two-dimensional geometric transformations. In that, the first it comes two-dimensional translation. Therefore, we are going to discuss two-dimensional translation. Now you can see in that figure a point P has been displaced, or you can say it's moved to another position Q, and the coordinate of P is x and y, and coordinate of Q x dash and y dash. Therefore, what will be the relation between x and x dash and y dash? And it is given that the tx, that means translation distances tx, that means it is in x coordinate, translation distance is in the x coordinate, and ty is translation distance in the y coordinate. If it is that, then the relation is that x dash is equal to x plus tx and y dash is equal to y plus ty, and the tx comma ty is called translation vector. Now this can be expressed in the matrix forms also, and most effective matrix form, the homogeneous coordinate matrix form. In that, the advantage of that is that you can see it has been added, tx has been added, but in the matrix form you can see the matrix and the multiplied form. Another advantage is that in case of a multiple translation, that means composite translation, we can have a one translation matrix, and all the effect will happen in the one matrix. That we'll discuss later. Therefore, homogeneous matrix form, you can see if you multiply that, you'll multiply the matrix, you'll get the original equations, and x dash would be x plus tx, and therefore these equations we can express in this matrix form. Now we'll take up one example of two-dimensional translations. Here you can see the point is 3, 4, and it is moved to another point 5, 8. And in that case, the translation distance of in the x coordinate is tx. From 5 minus 3 we get 2, and translation distance in the y coordinate 8 minus 4 we can get 4. Now this I express in the homogeneous coordinate form. You can see tx and ty has been replaced by 2 and 4, and this is my original point's coordinate. This is the x coordinate, this is the y coordinate, and this is the 1. You know that in case of a homogeneous coordinate, it's one dimension is incremented, and therefore if we multiply these two matrix, that means 1, 0, 2, if you multiply it with this 3, 4, 1, that means 3, 1 into 3 plus 2 into 1, will add it, will get 5. In this way also second row also will get 8, and then therefore you can see x dash will be 5 and y dash is equal to 8. In that, what I wanted to show here, if you know the translation distance and if you know the initial coordinate of the point, you can find the final positions coordinates, and that is the you can find in the with the help of a matrix, and in that homogeneous coordinates we can find it. Now we'll discuss two-dimensional composite translation, that means multiple translation. Therefore, from the original point it has moved to another point, from that point it moved to another point. In that way we have considered only two cases. First, from original position it moved to another coordinate, and then from that point it moves to another point. Therefore, two translations happens here. Therefore, here the tx1 and txy1 is corresponds to the translation distance for the first movement, and tx2 and ty2 is corresponds to the second movement. And therefore, you can see that these two, we are this in the matrix form. You can see homogeneous matrix form. So you see this is the first translation matrix form, this is the second translation matrix form, and this is the original coordinates. And if you multiply these two matrix here, then you come with single matrix where you can see translation distance in the x coordinate are added together and translation distance in the y coordinate are added together. And therefore, you can see the two matrix we are converting into a single matrix, and this is the transformation matrix, and that is the major advantage if you works in a homogeneous coordinate form. And then I'll take up an example here. Here you can see that 2D composite translation, the original point was 4, 5, it moved to 8.10, and then again it moved to 14.18. And therefore, in the first case, you can see 8 minus 4, that tx1 is equal to 4, and 10 minus 5, and ty1 is equal to 5. And in the second case, 14 minus 8 is equal to 6, and 18 minus 10 is equal to ty2 is equal to 8. And then we substituted here tx, and that is we substitute here in this case. First it is a tx1 is a 4, and ty1 is equal to we have substituted 5, and you can see tx2 it is a 6, and ty2 it is 8. Now if you multiply this matrix with this matrix, you are coming to a single matrix, and the single matrix, this is called ultimate transformation matrix. If you multiply with the original coordinate, you will get the final coordinate, and that is the very advantageous working with the homogeneous coordinate matrices. And that is all about the translation transformation.